Good afternoon, everybody. Seems like quite a few of us are here. I'll give just another minute or so for folks to come in. Today I want to do a few things. Of course, we're going to talk more about functions and their graphs, but before that, I also wanted to give a little bit of a review of some algebra properties that I'd be willing to bet most of you remember, but maybe one or two of them you've forgotten, and just to make sure we're off to a good start. So when I was structuring your homework, I included some stuff that I don't usually include in the first homework for MAC1140 because it's harder for me to get a feel for where you guys are at in this online setting. So let's get into it. This is pre-calc, section 4. This is a lecture. And today is the 26th. I will be having my first office hour today. Does anybody else? Gabrielle says she's not getting any audio. Can the rest of you hear me? If you can hear me, go ahead and give a thumbs up react. If you cannot, just leave it blank. Math you can hear. Okay, sounds like it's better. All right, good. There have been some problems with Zoom lately. It's been a huge headache. So I really appreciate you guys letting me know if there's something that is not working how it should be. So what are we doing today? Well, we're going to do a small algebra review. And then we're going to talk more about functions. Specifically about their graphs. So the sort of thing I'm talking about in your homework when I say I tacked on some problems that are not usually there, I'm talking about stuff like this. So, cleaning up messy fraction stuff and, writing things in inequalities. Kind of just a very, very fast overview of the basic algebra and arithmetic skills I'm expecting folks to have coming in here. So I want to grab just a few things like this. Number 4 looks like the sort of thing that might be worth talking about a little bit. Maybe a little something to do with inequalities. And then these power rules, those exponent rules are the sort of things that are going to be very important later in the semester. So I want to make sure we're all on good, solid ground. So a little algebra. If I asked you to write an inequality, equivalent to the statement, I'll do a few of these. X is negative. And maybe X is between 2 and 7. And maybe X is no larger than 5. Let's take a look at each of these. Some of this stuff is just vocab stuff. Like I've occasionally got calc students asking me whether 0 is positive or negative. And that's just a matter of semantics. Negative means smaller than 0, right? So 0 is neither positive nor negative. And if I tell you X is negative, that means X is smaller than 0. So the equivalent inequality to X is negative is X is less than 0. If I wanted to say X is between 2 and 7, that would mean X has to be strictly larger than 2 and also strictly smaller than 7. So I could write that as a compound inequality as 2 is less than X is less than 7. Or you could write x is bigger than 2 and x is less than 7. Either of these would be okay. Personally, I prefer this first guy. Okay, so being negative is the same as being less than 0. Being between 2 and 7, this is the nice way to say both at once, but you could also say it as these two separate statements. If I tell you x is no larger than 5, well, what numbers are not larger than 5? 0 is not larger than 5. 1 is not larger than 5. 5 itself is not larger than 5. So this is equivalent to saying x is less than or equal to 5. So now inequalities are something that are not given as much love as they should in the earlier algebra classes. And I just wanted to remind you a little bit how these work. Remember, this is less than. So A is less than B means this guy is strictly smaller than this guy. This is greater than. This is less than or equal to. And this is greater than or equal to. There's a few little things like this in the homework. Like I said, just want to give you a little bit of practice, make sure we're all on the same ground. I don't want to bore you at the same time, so unless there are questions, I won't spend any more time on this sort of thing. Any questions about how you go from a statement like this to an inequality like this, or a statement like this to an inequality like this? Okay, moving on then. Another one of the things that I know a lot of folks kind of run away from is fractions. Fractions, especially when things get a little bit complicated. So how do we clean up something like this? Fractions are, of course, made up of division, right? Division of integers, division of numbers in general. And division is not associative, it's not commutative, it's not a nice operation. Order matters a lot. So what I would encourage you to do whenever you encounter some big messy fraction thing is to think about the overall larger fraction and then its components. So here, this big long fraction bar determines the overall fraction. So the numerator of the big fraction is 3, and the denominator of the big fraction is 4/5. Once you have those recognized, put them in parentheses. You'll never mess up one of these compound fraction things again if you do it like this, I promise you. And then we'll do the same for this one. This big long fraction bar separates the overall numerator from the overall denominator. So the overall numerator there is the fraction 1/3, and the denominator there is 7. And then you have to remember all those rules, right? So 3 divided by 4/5 is the same as 3 times 5/4. So when you divide by a fraction, you flip and multiply. If this was a 1/3 or some other fraction upstairs, that fraction would be left alone here, and we would be multiplying by the reciprocal of that denominator. And then from that we'll subtract. So here, this is 1/3 is my numerator, so I'm going to leave him alone. And I want to divide that by 7, so that's the same as multiplying by 1/7. Stuff like this might feel trivial. It might be like, oh yeah, I know how to do that. I would never forget that. But you'd be amazed at the mistakes I see. So I just wanted to spend a little bit of time making sure we're all on the same page. So recognize the longer fraction bar as a grouping symbol, and then put the individual numerator and denominator in parentheses. even if they are themselves fractions. That little intermediate step of putting in these parens can save a lot of headaches. From here, the free is the same as 3 over 1. I would multiply straight across. So 3 times 5, that's 15 fourths minus, again, here, I'll multiply straight across. I'm following the order of operations doing the multiplication before the subtraction. So 1 times 1 over 3 times 7, that's 21. And then if I wanted to combine these into a single fraction, I would need a common denominator. Now 4 and 21, I don't think they share any factors. 4 is 2 squared, 21 is 3 times 7. So the only choice for a denominator there would be 4 times 21. So I'll multiply this guy by 21 over 21. And then I'll multiply this guy by 4 over 4. I'm not changing the value of the 15 fourths because this is equivalent to 1. I'm just multiplying by 1. 21 over 21 is 1. Similarly here, I'm not changing the value because 4 over 4 is equal to 1. 15 times 21, I don't know off the top of my head. I don't want to burn time. What? No. No, I am burning time. 315. So this is 315 over 4 times 21 is 84 minus 4 over 84. So then we just get 315 minus 4 is 311. Hey, that's a nice number. Over 84. Okay. And the other kind of review-ish stuff I put in your homework has to do with rules for exponents. And those are important enough that I'm going to take some time to actually write them out rather than just doing examples. So a few things that I'd like to make sure everybody has in their notebook, they can refer back to them, and hopefully remembers forever, are the following rules for exponents. If you have two numbers, say a to the b and a to the c, and you want to multiply them, you can just add the powers. This is a to the b plus c. If you happen to be dividing them, a to the b over a to the c, that's the same as a to the b minus c. You can subtract the powers. And this last one is a little bit funny. If you take a number like a to the b and you raise that whole thing to the power c, that's the same as a to the b times c. And then maybe one last thought is that the nth root of a number is the same as that number raised to the 1 over nth power. So these basic rules for exponents will get you through the rest of those little review problems. For example, I'll take a look at 1 or 2. Did I not leave that open? No. Why? 1140. I thought I had this out. Come on. Yeah, so like 2 to the 3 times 2 to the 7, that should be 2 to the 3 plus 7, which is 2 to the 10. And it's way nicer to write it like this than it is to figure out what each of these are and then multiply them out the long way. That would take forever. Much nicer to just think of it, oh, it's 2 to the 10. Or if I wanted to write, you know, the cube root of 5 to the 18, I could figure out what 5 to the 18 is and then try to take its cube root. But that would take forever, and finding cube roots is kind of tricky. So it's much nicer to use these exponent rules. I'll say, okay, well, that's 5 to the 18, all raised to the power of 1/3, because this is the third root, or the cube root. And then I can use this rule. I can say, oh, okay, well, 5 raised to the 18, all raised to the 1/3, is 5 raised to the 18 times 1/3. And 18 times 1/3, that happens to be nice, right? 18 divided by 3, what is that? That's 6. So this number is the same as 5 to the 6. So I hope that you guys don't resent me for putting those on there. Like I said, I don't really know what everybody's background is like coming into this, and I wanted to make sure we had a common understanding. But the rest of what we want to do today is working with functions. So let's return to that. Last time we looked at some piecewise functions. We drew some graphs. I'd like to do a little bit more of that. A little bit more practice graphing piecewise functions. So let's say, can we sketch the graph of the piecewise function f of x is, let's say it's -2 if x is less than or equal to -4. It could be maybe x plus 1 if -4 is less than or equal to x is less than 0. Maybe 1 minus x squared if x is greater than or equal to 0. So I could start by making a table. No one on earth can ever stop you from making a table of values for a function. But I would like to get a nice picture of this graph without going through all of that painstaking stuff. So the trick is to think about 3 graphs. Think about the graph y equals 2. Think about the graph y equals x plus 1. Think about the graph y equals 1 minus x squared. Each of these graphs we know pretty well. Y equals -2, I'll put here. Y equals x plus 1, I'll put here. And y equals 1 minus x squared, I'll put over here. So y equals -2. That's a constant function. It's a horizontal line, right? Right down here. Y equals x plus 1. That's a linear function whose slope is 1 and whose y-intercept is 1. So he looks like, we go through here, we go through here. He looks like this. And 1 minus x squared, that's a parabola opening down whose vertex is at 0, 1. Having x-intercepts, plus and minus 1. So he looks something like this. So these are my 3 pieces that we're going to chop up and glue together to make the graph of this function. My formula for f says f of x is equal to -2, i.e. looks like this guy, if x is less than or equal to -4. So I'll come down here, start drawing my big graph, f. And I'll mark this as 1, 2, 3, 4, so that's -4. I'll mark this as like 1, 2. So the line y equals -2 would be the horizontal line running here. But my function only behaves like that if x is less than or equal to -4. So right here at -4, and everywhere to the left of that, f of x just looks like this. Now between -4 and 0, f of x looks like x plus 1. That's like this. All right, so I would take the part of this graph that is between -4 and 0, and I'll hold on to that. Well, when x is -4, this would be -4 plus 1 is -3. So we'll start down here. Oh, and this should be, I'm sorry, this should be a strictly less than, not less than or equal to. So we'll start down here. And when x is getting close to 0, this guy is getting close to 1. So I'll put this mark up here, and that's what I'm shooting for. And then this piece looks like that. And now if x is greater than or equal to 0, my function looks like 1 minus x squared. That's this piece. So I'll take just this piece here. When x is equal to 0, this is 1, so that fills in this hole. And then we'll have our little parabola piece here. So that's what the graph of this function would look like. I know that graphing piecewise functions might be new to many of you. I think college algebra classes at Santa Fe don't often discuss piecewise functions in a lot of detail. So I'd like to take a second and really make sure we're comfy with where this picture came from. So what would you guys like to know? What are we thinking? What feels weird? What feels good? What feels bad?
I have a question about the first graph.
Sure.
The one that it's y equal, is that a 2 or it's -2? I can't see.
-2, sorry.
So on the graph, is it on the negative side or is it in the positive side where you draw the line?
So this line right here is the line y equals -2.
Okay.
So it's think of it as y
Upside down?
0x plus -2, right? That's really, you can think of it as a linear function whose slope is 0 and whose y-intercept is -2. So 0 slope means horizontal, and then the y-intercept is -2, tells you it's got to go through this point. So it's got to be this line. But then I just take the part of it where the x values are less than -4.
Oh, okay, now I see it.
And that's the part that I bring down and make a part of my graph here.
Yeah, thank you.
Of course, of course. Yeah, what else are we thinking?
Can you go for it just one more time? Because I'm kind of like lost a little bit.
Yeah, so what we did there is I drew the graph of each of these pieces on their own. And then I just took the parts of those graphs that this function told me to use. So this function said, okay, well, if x is less than or equal to -4, behave like the line y equals -2. So for x is less than or equal to -4, I had that guy.
Okay.
For x is between -4 and 0, behave like this guy. So that's this piece. And then for x is bigger than 0, behave like this parabola. So I take this graph, but just the part where x's are positive. We'll go through another example after this. I think it's good to do a few. So if it's still not feeling 100% clear on this guide, just make sure you get everything written down, and then we'll go nice and carefully through another one, and I'll bet it will click.
All right.
Let me grab one of them from your homework. I think I asked you to do a few of these. I'll get this out of your way, so if you're still writing, you can see. let's see. Yeah. Tables of values are good. But you know what's better? Yeah. Let's do number 44. Your numbers may vary a little bit from mine, but I'll start with this. So x and x plus 6 split at 0. Right, like that? Yeah, okay. So my two pieces here in this piecewise function, one of them is x and the other one is x plus 6. So what I want to do is start by just graphing those two functions on their own. Y equals x, okay, well that's a line through the origin with slope 1. I know what he looks like. Looks like this. And y equals x plus 6, that's a line with slope 1 whose y-intercept is all the way up at x equals, or y equals 6. So he looks like, 1, 2, 3, 4, 5, 6. He looks like this. So these are my two pieces. I want to then figure out which part of each of those graphs I'm going to grab. So imagine you could come in here with some scissors and cut this graph and then just take half of it. Cut this graph and just take half of it. Then stitch those two halves together, set them so they overlap. That will be the graph of f. So f of x behaves like x if x is less than or equal to 0. So that means I'm going to take this bold piece here and throw everything else away. Because this is the part where x is less than or equal to 0. Over here, x's are greater than 0, right? Like x is 1, 2, 3, 4, 5. Those are all greater than 0. But over here, x is like -1, -2, -3. Those are all less than 0. So this bold piece here is the piece I'm going to keep from the first graph. And then I come back to f of x. It says, okay, it's going to be x if x is less than 0. That's this piece. It's going to be x plus 6 if x is greater than 0. Okay, well, here's y equals x plus 6. Let's take the part of this where x is greater than 0. That's everything to the right of the y-axis. And I'm not going to take the point here where x is exactly equal to 0 because I just want x's which are greater than 0. So now that I've graphed my two pieces, I recognize which part of those graphs I want to keep. From the first graph, I want to keep the part where x is less than 0, that's these. And from the other piece, I want to keep the part where x is greater than 0. So now I imagine I could come in here with some scissors and chop, 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 chop this, and just hold on to this piece. Chop, 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 chop this, and then just hold on to this piece. And then I set the two on top of each other. That will be the graph of f. So I take this piece, and then just this piece. So 1, 2, 3, 4, 5, 6. This big graph down at the bottom, this is the graph of f. Do you see how we did that? How we took those two pieces, cut them up, and then stacked them on top of each other? So this is the line y equals x plus 6, just the part where x is greater than 0. And this guy, he's the line y equals x, just the part where x is less than 0. We take those two pieces and we put them together. That gives us the graph of our piecewise function f of x. I'll do one slightly harder one, but then we're going to move to something a little bit different. So first, any questions about where the big graph came from? How I got it from the smaller graphs? Okay, let me grab one more here. Sure, why not? Okay, so let's sketch f of x equals a piecewise function, 7 minus x squared, if x is less than or equal to 2, and x if x is greater than 2. So I'll start with a graph of each piece, y equals 7 minus x squared. What does that look like? Okay, well, that's a parabola opening down, whose vertex is at 0, 7. So he looks like this. This is 0, 7 up there. And then y equals x, that's that line through the origin of slope 1 again. And then I want to identify which piece I want to hold on to. So maybe 2 is like right here. And if x is less than or equal to 2, okay, well, that's everything to the left of 2. So I'm going to take this part of my parabola and 2, and this part of my line. So the graph of f of x will look like this guy to the left of 2, and he'll look like this guy to the right of 2. So if I stitch those two things together, imagine I could just cut them out and set them right on top of each other. What would that look like? There's 0, 7 up there. If I plug in 2 for x, here I get 7 minus 4, which is 3. So that'll be here. So the piece of my parabola that I get to keep is all of this. And then the piece of my line which I get to keep is just this stuff, which would be something like this. I feel like we can see the connection there. So draw the pieces individually and then figure out which part of each piece you want to keep. and then stitch those two together. So this is 1, this is 2. 2 is the place where we are splitting up our pieces. If x is smaller than 2, that means if we're looking to the left of the vertical line x equals 2, f of x plays like this parabola. So that's the part of that parabola that gets carried over onto the final graph. And if x is greater than 2, then f of x plays like this line. So this is the part of this line that gets carried over to our graph. So it's a cut and paste thing. You cut and paste, or copy and paste, parts of each of the graphs onto the final graph. You feel comfy with where this picture came from? How we got it from these two pictures? Should ask, are there any questions about how we got this picture from these two pictures? Okay, I will take your word for it. So last time we left off looking at graphs of piecewise functions, and we said the next few things we're going to do are trying to start getting information out of graphs of functions and also trying to get really good at understanding function notation. The other thing that you have a lot of in your homework this week is just working with function notation. So that's what I would like to talk about now. So how do you find things like f of a plus h or f of 1 minus x? Well, what's the relationship between f of x squared inside and f of x all squared outside? I'd like to highlight some of those differences and try to get you guys comfy with the notation. And we'll do that by playing with some examples. So let's let f of x be x squared minus 1. And then we're going to find and compare f of 2x and 2 times f of x. F of x squared and f of x all squared. And let's do f of x plus 2 and f of x plus 2, like this. So just trying to get comfy with what this notation means. Remember, you can think of the function as the rule or the machine that takes the input x and sends it to the output x squared minus 1. So whatever's in the parentheses here is what the machine is eating. And then whatever you put on the outside, whatever your result is, that's what the machine is spitting out. So here I want to feed the machine f the input 2x. Well, what does f do? Whatever you feed it, it squares that and then subtracts 1. That's the verbal description for this function f. It squares the input and then subtracts 1 from that result. So if I feed it 2x, it will square the input 2x and then subtract 1. So in other words, to find f of anything, you just take the formula and in parentheses, replace x by whatever the thing is that you want to find. So if I want to find f of 2x, that will be, okay, f of x is x squared minus 1. So f of 2x is 2x all squared minus 1. And we can work with that a little bit. 2x all squared is 2x times 2x, which is 4x squared. And then the minus 1 is the minus 1. Any questions about that first line? How we get f of 2x to 4x squared minus 1? the top here, it says, find and compare. So I'm going to compare this to this. I'm going to compare this to this, and so on. I'm going to compare this to this. So this is f of 2x. Do we think it's going to be the same or different than 2 times f of x? Can this 2, in other words, be popped out? I think in our minds, oftentimes this kind of looks like multiplication. It kind of looks like f times 2x. And if that was the case, then the 2 could come out. But what we need to remember is that this isn't multiplication. This is function notation. This is the function f having been fed the input 2x. And there's not necessarily any reason for that to be the same as 2 times f of x. So let's see what we would get here. F of x, oh, well, I know what that is. So 2 times that should be 2 times, and what is f of x? Well, here this is a single thing. This thing is x squared minus 1. So that's 2 times parentheses x squared minus 1, which is 2x squared minus 2. So you see, these are not the same, right? They're quite different. Here I want to take the output from f of x, which is x squared minus 1, and multiply that by 2. So I take x squared minus 1, and I'm putting it in parentheses here because it's being represented by this single symbol, and then multiplying by 2. So these are not the same. And in general, f of 2x or 5x or 10x is not going to be the same as 2 or 5 or 10 times f of x. Separate animals. Questions about this first piece? Is everybody comfy with why that first guy became this and why that second guy became this? Okay, so if there aren't any questions, I'm going to move to this second guy now. If I want to find f of x squared, that means I come back here and everywhere there's an x, I'm going to plug in x squared instead. So this should be x squared squared minus 1. And according to our rules for exponents, x squared squared, that's the same as x raised to the power of 2 times 2, or x to the 4 minus 1. On the other hand, if I want f of x all squared, okay, well, what's f of x? F of x is x squared minus 1. If I want that all to be squared, I'm going to have to FOIL. That's x squared minus 1 times x squared minus 1. Anything squared is that thing times itself. So the x squared minus 1 squared is x squared minus 1 times x squared minus 1. And now I FOIL my first x squared times x squared, that's x to the 4th. My outers are minus x squared, my inners are minus x squared, so I get minus 2x squared. And then negative 1 times negative 1 is plus 1. So these are also not the same. Squaring on the inside and squaring on the outside give totally different things. For this last guy, f of x plus 2, I'll come in here and everywhere there's an x, I'll write parentheses x plus 2 instead, so that'll be x plus 2 squared minus 1. And here I should FOIL, so this will be x squared plus 2x is plus 4x. And my lasts are plus 4. And then I've got my minus 1. And then there's some like terms I can combine. The plus 4 and the minus 1 here make a plus 3. So this is x squared plus 4x plus 3. On the other hand, f of x plus 2, well, f of x is x squared minus 1, and then I want to add 2 to that. Well, that's not so bad. That's just, okay, I've got a common or a like term there, the minus 1 and the plus 2. That's x squared plus 1. And so these are also not the same. Very common first few questions on my, very common questions on my first MAC1140 pre-calc exams have you comparing things like these. Because we're going to start building big complicated objects out of stuff that looks like this, and we'll need function notation to describe those things. So it's important that we're comfy. Questions on where any of these came from, how I found and simplified any of these objects, or why we started the way we did, why I wrote things the way I did, any of that stuff. So an example then of something that we would build using this notation, let's find and simplify the difference quotient, f of a plus h minus f of a all over h for this function f of x equals x squared minus 1. So I need to know what f of a plus h is. I need to know what f of a is. Then I'll subtract those and divide everything by h. F of a plus h, I get that by taking my formula for f, which is over here. And everywhere there's an x, I write parentheses a plus h instead. So this is a plus h all squared minus 1. That's, if I FOIL this out, a squared plus 2ah plus h squared minus 1. And now we can really get rid of these parens because we've done all of the exponent work there. So this is just a squared plus 2ah plus h squared minus 1. F of a, well, I just take my formula for f over here, and I swap the x for an a. So that's just a squared minus 1. Sure. So the in-between step here was to write out a plus h squared. I had to do some foiling there. So while you're writing, I'll add this little detail maybe. If we FOIL, my firsts are a times a is a squared. My inners and outers are both ah. And then my last h times h is h squared. So this is the same as a squared. HA and AH, they're really the same thing. That's just plus 2AH. There's 2 of them. And then I've got my h squared. So this object is called a difference quotient, and it's a nice way of measuring slope. You'll work a lot with this sort of thing at the start of Calc 1. So remember, the task at hand is to find and simplify this. So far I've got this guy and I've got this guy. So what's left to do is to subtract them. I have to take this, which is this, and then subtract this from it. And again, there's an individual symbol here representing things that have multiple pieces, so we'll want to put them in parentheses as we go to work with them. So f of a plus h minus f of a all over h. I'll take f of a plus h, which is this, and subtract f of a from it. And f of a was this. And then divide everything by h. My next move, if I want to simplify this, which when I plug in, I get this, is going to be to distribute this negative. And that's why these parens are so important. So that would be a squared plus 2ah plus h squared minus 1. That's that first piece. And there's nothing multiplying him or being done outside, so I can lose those parens. In order to lose these two parens, I need to distribute this negative. So that will be minus a squared plus 1. And everybody's still getting divided by h. And now I'll look for like terms, things that can be combined. I have a positive a squared here and a minus a squared here. So those will eat each other up. I've also got this minus 1 here and this plus 1 here. So those will eat each other up. So these go and these go. So what we get, the stuff that survives, I've got 2ah plus h squared all over h. I can factor an h from the numerator here, and that will give me 2a plus h left over. And now that I've factored this h, I can cancel it with the h downstairs. And I find that my difference quotient here simplifies to just good old 2a plus h. Lily asked a question in chat earlier that I didn't see. What's the function x squared? Could I ask you to clarify a little bit that question, Lily? Okay, cool. Ah, I see. Okay. So how do we feel about this difference quotient? Are there any questions about how f of a plus h became this piece? Yeah, we'll absolutely do another example. Any questions about why either of these objects were what they are here? Feel comfy with that? And do we see how we're plugging them in here? This piece is f of a plus h. This piece is f of a. So I want to subtract them. That's this. And then divide by h. Yeah, we'll do a few more examples. Last call for questions on this particular example. Okay. So let's let g of x be 1 over x. Which of the following is equal to g of a plus h? So I'll give you a few choices. We can have 1 over a plus h, 1 over a plus h, or maybe 1 over, trying to think of other ways to do this weirdly. Well, maybe I'll just let you choose between these two. Which one of these is this? Is it number 1 or number 2? You can answer in chat or you can just shout out. Remember, you can hold the space bar to talk.
It's 2, right?
It is 2, yeah. Yeah, Matthew and Lily are correct. So the formula for g is you just take whatever you feed it and put it downstairs in a fraction with 1. So g of anything is going to be 1 over that thing. So since the input here is a plus h, the output is 1 over a plus h. This guy, how would I represent him in this function notation? So this one is g of a plus h. What is this though? Could we write that in terms of g of x? Could we write something kind of like this that would be true for this? What about just this piece right here, the 1 over a? What is that in terms of the function g? Well, if I plugged in an a here, then that would mean an a goes here. Yeah, that's g of a. So this thing here, this is g of a plus h, like that. And what we see is that g of a plus h on the outside is very different than g of a plus h on the inside. That's the connection to what we were doing in the previous example there, where we wanted to compare those different function statements. So this guy is g of a plus h like that. This guy is g of a plus h. So if I wanted to do a difference quotient thing, like the previous problem, where I find and simplify g of a plus h minus g of a all over h, I would start with this piece for g of a plus h. Since g of x is 1 over x, g of dog shit would be 1 over dog shit. G of a plus h is 1 over a plus h. So this piece is 1 over a plus h. And then g of a is just 1 over a. And then I want to divide everything by h. And you see some of these weird sort of fraction things showing up like we talked about at the start. So this is the first time we've looked at an expression like this. How could I clean up this big nasty fraction? Yeah, I need a common denominator. So I'll think of this piece is my top, this piece is my bottom. And I can start by doing the flip and multiply thing. So I'd have dividing by h, that's the same as multiplying by 1 over h. And then the rest of that looks like this. So if I'm hoping to clean this whole expression up, I need to combine these two fractions into a single fraction. And the way to do that is just like Olivia said in chat, by having a common denominator. Now these aren't made up of numbers, so there's no like finding the least common denominator. They're made up of algebraic symbols. So the only possible choice for a denominator is a plus h times a. I still have my 1 over h out front. And then I'll have here, this piece, if I want to write him with the denominator a plus h times a, he'll need to be multiplied by a over a. So I'll write this as 1 over a plus h times a over a. And this piece, he's missing the a plus h factor. So I'll have minus 1 over a, that's that guy as he was, but he needs to be multiplied by a plus h over a plus h. And we should do that in parentheses. And notice how I'm not leaving off any part as we go from step to step, you know, step 1, step 2, step 3. I've still got the divide by h going on here as my multiply by 1 over h. I've not like thrown him away. I'm keeping everything nice and organized. This piece is this piece, and I'm multiplying him by a over a because he was missing the factor of a in his denominator. This piece is this piece, and I'm giving him a factor of a plus h downstairs because he was missing that. When I multiply these two fractions, say these two fractions, the denominator will be a plus h times a. And now when I multiply these two fractions, their denominator will also be a plus h times a. So that will give me the common denominator that Olivia said we needed, and then we'll be able to see where to go from there. My 1 over h out front still hanging on. And now inside my big parens, I'll multiply these two fractions, just top times top, bottom times bottom. That will be a times 1 upstairs, and a plus h times a downstairs, minus this guy. When I multiply these two, the numerator will be 1 times a plus h, that's just a plus h, over my denominator is a times a plus h. Now people like to ask, could I cancel these a's, or could I cancel this a plus h? Yes, you could, but you don't want to. That would take you back to this step. Remember, the whole reason for doing this is so we can combine these. Now that they have the same denominator, we can go ahead and subtract them. So I can write this as a minus parentheses a plus h all over a plus h times a. And remember again, the fractions are grouping symbols. So you always think of the top and bottom of a fraction as being in parentheses. That's where these parens come from. And without these parens, we'll end up off by a negative sign, and much worse can happen. So any questions about getting to this step? Okay, then I'll go ahead and distribute this negative. I'll get 1 over h times a minus h all over a plus h times a. That's the same as 1 over h times a minus a. Well, that's 0. So I'll have minus h over a plus h times a. And now I'm multiplying these two fractions. I can multiply straight across. That'll be 1 times negative h, well that's negative h. And downstairs I'll have h times a plus h times a. And we can cancel the h's. So we get negative 1 over a plus h times a, like this. Let's see. If I distributed this a times a plus h, that would be a squared plus ah. And you could do that, although it's not necessary for the purposes of the problem. Make sure you give the a to both the h and the a. But yeah, that would be okay as long as you get a squared plus ah downstairs. You could write that as negative 1 over a squared plus ah. Yeah, that would be fine. Okay. I think we're getting a little bit close to the edge of our class time here, but I'd like to work one more problem where we play around just a little bit with function notation in this same sort of way. Okay, Lily, yeah, go ahead. Oh, yeah, good question. All right, let's work that into our last example. So here I have f of x is x squared plus x to the negative 2. So x to the positive 2 plus x to the negative 2. I can't combine these. They're not like terms. One thing you can always do with a negative exponent is rewrite it using positive exponents. So the x squared stays x squared, but x to the negative 2, I could rewrite that as the reciprocal of x squared, like this. So the general rule here is that a to the negative b is the same as 1 over a to the positive b. That's the kind of general rule for exponents. Let me see, I'm not sure if I can slide because I think it's on the reverse side, but I can leave this here for a second longer. Okay, so just a second longer for anybody who's still writing. And then we'll do something similar, but maybe a little bit smaller with this last guy. All right. So here I do have a negative exponent, and I could rewrite it like this according to this rule. That's an option. Let's see if we can't compute a few nice things here. Let's find f of 1 plus a, and let's find f of f of x cubed, like this. So 2 parts. For part 1, if I wanted to find and simplify f of 1 plus a, I would start by everywhere there's an x, writing 1 plus a instead. So this would be 1 plus a squared plus 1 plus a to the negative 2. The 1 plus a squared, I could FOIL all that out. That's 1 plus a times 1 plus a. And this guy is the same as having 1 over 1 plus a squared. So that's 1 over 1 plus a times 1 plus a. because this piece is the same as 1 over 1 plus a all squared. So then I can do some FOILing. This will be 1 squared plus 1a plus 1a is plus 2a plus a times a is a squared. And then this piece would be the reciprocal of that. 1 times 1 is 1, 2a plus a squared, like this. And that's as nice as that's going to get. If you wanted to combine these, you would have to have a common denominator. Right now, the denominator of this piece is 1. So there's no really making nice here. You could, but it's going to end up with a 4th degree polynomial upstairs. Quick question. Is 1 over 1 plus 2a plus a squared the same as 1 over 1 plus 1 over 2a plus 1 over a squared? Can I split up fractions across their denominator like that? Is this kosher? It's tempting, right? But when in doubt, you can always ask yourself some questions like, okay, is 1 over 2 the same as 1 over 1 plus 1 over 1? Well, this is 1 plus 1. So this side is 2. This is 1/2 though, right? Which is much smaller than 2. So no, so that's not kosher. And for the same reason, no, this isn't kosher. So we can split up fractions across their numerators. That works great, but you cannot split them up across their denominators. In fact, if you wanted to add stuff like this, you would have to have a common denominator among all 3 pieces, and it definitely wouldn't come out looking like that. So there's really not a whole lot we can do with this, and there's not a whole lot we can do with this. So this is where I would say this is fine. What about part 2? How would I find f of x cubed? No, it's gone off the camera here. We can't quite see it. F of x, remember, is x squared plus x to the negative 2. So this would be x cubed squared plus x cubed to the negative 2. And my rules for exponents work great, whether the exponents are positive or negative or whatever. So I can still do that multiply thing. I've got a power raised to a power. So that's x to the 3, all raised to the 2. That's the same as x to the 3 times 2 is x to the 6. Plus x to the 3 to the negative 2. Well, that would be x to the 3 times negative 2. That's x to the negative 6. And then if you wanted to rewrite with positive exponents, you could, as x to the 6 plus 1 over x to the 6. And then what if I wanted to combine these into a single fraction? Could I do that? Is there a way to put these together into one fraction? For sure. What do we need?
You see a common denominator? So
Yeah, exactly. Yeah, perfect.
Yeah.
So this guy has a denominator of x to the 6. Right now, this guy has a denominator of 1. So I take this first piece and I multiply by x to the 6 over x to the 6. And this other guy, I just leave him alone. He already has the denominator x to the 6. And then I'll continue it over here. This piece, x to the 6 is really over 1. So when we multiply these two fractions, I'll get x to the 6 times x to the 6 upstairs. That's x to the 12 over x to the 6. And then this guy is just plus 1 over x to the 6. So that would be, now that the denominators are the same, I can combine them into a single fraction. That's just x to the 12 plus 1 over x to the 6, like this. So in this first part of pre-calculus, the most important thing is that you get comfy with function notation. What the hell do we even mean by f of x? It's something that a lot of us in algebra classes, just we write y instead and then pretend like it doesn't matter and we don't care. But in calc, the function notation is everything. We describe all of the operations, processes, and patterns in terms of this function notation. So playing around with those questions in the homework, making sure that you do them on your own and you work them until you're comfy with them is super important.
I have a question.
Yeah, Matthew.
On that last part where it says x to the 12 plus 1 over x to the 6, according to the exponent rule, can't that be reduced at all?
Well, there's no factor of x to the 6 here.
Oh, okay. So, okay.
If there was, a good rule is that in order to cancel anything, you have to have it as a factor of the top and a factor of the bottom.
Okay.
There are definitely lots of x's here that I could cancel with some of these x's if I could factor them. But because this piece doesn't have any x's, I can't factor any x's before to cancel them.
Right, that's my bad. All right.
No, you're okay. You're okay. It's a super common thing too. And the rule I like to tell my college algebra students, never cancel anything top to the bottom unless your previous step was factoring that thing. So if you can grab something out as a factor of the top and a factor of the bottom, then you can cancel it, but only then. So yeah, fair question. We could have done what we did down here, we could have done here also. It would have just been very messy. I think I have the number of attempts per problem set to 55, which is the max on WebAssign. So you're never going to run out of attempts. You can keep trying them until you get them. If you do manage to run out of attempts, let me know. But it hasn't happened yet. So yeah, don't stress about that. Take your time, work through them. Don't feel any pressure to like, oh, it's my last attempt. I got to put it in Symbolab and make sure it's right. There's nothing like that. Take your time. I don't want you guys to lose points on the homework. It's just there for you to practice. That's the intent.
Excuse me, Professor.
Yeah, yeah.
Can you go back to the problem we did before? I was missing a part.
This guy?
Yeah.
Sure.
Yeah, it's that one. Let me take a picture. Thank you.
Thing there? Yeah.
Yeah, I forgot the last part.
All right. Okay. Anything else before we round off the day, guys? Okay, then before I let you go, I just want to show you how to come to the office hours in case you want to. I do recommend doing it, especially as we get closer and closer to test time. Office hours are very important. So you'll come in Canvas to our class here, which is MAC1140.004. And then you'll see I modified the office hours section. So whereas it used to say, just TBA and Zoom, now there's a link for the Monday, Wednesday office hours. So if you want to join that, if you want to go to the Monday, Wednesday office hour, just come here and click this first link. And there's a separate link for the Tuesday, Thursday office hours. You click here to join those. So these will take you to Zoom waiting rooms. And during those hours, I will always be monitoring those waiting rooms and bringing people in to talk about problems or do whatever it is they want to do. I am going to add a few more before the end of the week. I'm just trying to add them in the most efficient way. And then if you want to meet me outside of those hours, you can just send me a Canvas message. And I'd be happy to schedule an office hour that fits your schedule if these are not working for you or if we need more time. Alrighty.
Thank you.
Of course. Yeah, I hope you guys have a lovely rest of your day, and I will see you on Friday. Make sure you work on those books.
Thank you.
Of course. Take care, guys.